again. Very nice to see so many of you here. This is the University of Bristol hosted Alan Turing Institute Seminars in Urban Analytics. This is day 4 of 5 days of events that we're supporting here at the University of Bristol to showcase the work of Turing Fellows. And today we're focusing on urban analytics, and it's a huge pleasure to welcome our speakers today. Just a little bit of housekeeping. We are going to be recording this and it will be hosted probably on the Alan Turing Institute website at some point, so you might want to turn your video off for the duration. We're going to be using Slido for question and answers, so each speaker has roughly a half-hour slot, so we've got time for the talk and also some questions. So if you could post your questions in Slido, and then at the end of each talk, I will share that section and ask the questions, and we hope to get a dialogue going in that way. This is also to let you know that this is one event in a whole host of events that the Turing are putting on, which really run all year, and up until December. You'll find many more events that may be of interest to you. Please do take a look at that program, and Lily's going to put the link in the chat so that you can see all the kind of exciting talks and other workshops and activities that are going on at the Turing that you might want to take part in. Please take a moment to read our Jean Golding Institute Code of Conduct for online events, which Lily is going to put in the chat. It's really important that we all have respect for our speakers and for each other in these online events. Thank you very much. So, without any more ado, I'm going to hand over to our first speaker. So this is a paper co-authored by Dr. Levi Wolf and Sean Fox. It's going to be presented by Levi this morning on consistent urban areas for global urban polimetrics. Over to you, Levi.
Great, thank you very much. Let me share my screen. Can everybody see the slides here?
Yes, that looks great.
Okay,
thank you.
Cool. Thank you very much. Cool. So my name is Levi John Wolf. I'm here today to present a little bit about the work I've been doing with my colleague and fellow Turing Fellow, Sean Fox, and our field research assistant, Nick Dorward, on seeing urban fractionalization from space. It's a work in progress. We, as we'll discuss, have had some interesting twists and turns over the last couple of years. So I hope to at least tell you a good story about how the project went and is going now. So in the urban analytics program, of which many of the people in this, this particular seminar are participating, we like to talk a lot about sort of buildings, and we have this metaphor about building a future, and a lot of us actually indeed study city footprints and structures. Some people call this urban morphology. But the project that Sean and I have proposed is much more about the governance of cities rather than the building per se. So oftentimes when you have to build, you need a permit. So there's a lot of work over sort of classic political science about the way in which metropolitan areas, as they used to call them, but cities are governed. And so a classic paper in this literature focuses on this problem of metropolitan government. And it focuses on the fact that usually city governments do not have a single legal entity that's responsible for kind of controlling the way that the city moves, is planned, and evolves. So this is kind of, as this Ostrom paper suggests, that these governments are considered incapable of resolving these diverse problems of the wider metropolitan community, this sort of general functional urban area. And in particular, there are kind of two classic, what they call pathologies of urban government that are relevant in this case. So the first pathology is this duplication of function, and the second is kind of this concept of overlapping jurisdiction. Of course, back in the 1960s, there was kind of a concern that the identification of these sort of pathologies should not necessarily precede empirical work identifying the actual effects of these pathologies. So there was a lot of kind of theoretical debate, and there's been a lot of empirical progress on sort of how cities are planned, how cities are governed. So as I kind of alluded in the title slide, the way that this literature has evolved has focused on this concept of fractionalization. And fractionalization is this kind of pathology that I mentioned in the Ostrom paper, this pathology of metropolitan government, when authority is divided between multiple, what they call influential agents. So to break that down a little bit, actually, I guess I have some examples. So fractionalization has these kinds of multiple authorities having influence over a city. And we see the effects of the way that this authority is split in a couple of different areas. So we see that in some cases, incentives for governments to hoard resources may differ over time and space. And this can seriously affect sort of the responsiveness and efficacy of government. Second, urban sprawl actually can be harder to constrain if urban government is sort of strongly split over the city. So many different government agencies controlling different parts of the city. This can have a severe impact on planning decisions, on energy use, on transit efficiency. So it's important to try and understand how the sort of dispersion of authority in a city affects its human structure. In this World Bank report by Juan Carlos Duque, their study of Latin American cities, which were sort of generally speaking less developed and usually not as old, find that there actually may exist an optimal level of government fragmentation in these cities, where smaller governments that split the city may actually be more responsive to those parts of the city, but the coordination costs between just a few of those governments may be low enough that you get this benefit of efficiency, but you don't necessarily get too many people in a room at once when trying to coordinate. So going back to this concept of fractionalization and the classic model of how cities are split by their governments, we have two separate ideas. This overlapping jurisdiction, where a city system is split by two or more agents whose authority, whose territory overlaps. So in this idea, you can think of kind of a homeowners association, a historical preservation society, and the city council all might have to agree in order to renovate a historic property. So you have to get everybody in line in order to agree that you can do something. And in this kind of model of thought, there's not necessarily coordination that has to happen between the homeowners association, the preservation society, and the city council. It's just that there are multiple kind of different governmentalities that you have to deal with when you're trying to do something in a city. An alternative of this kind of idea is the duplication of function part of fractionalization. And this generally deals with the fact that a city system is split between two or more agents that exert authority over different geographical parts of the city. Their territory may not necessarily, in this case, overlap. And this is kind of the classic coordination or collective action problem scenario. So it invokes these kinds of situations where maybe you're citing an intercity rail system, and in order for you to do that, you have to coordinate between all of these different governments that control little pieces of the city. So in order to build effective infrastructure and plan, you have to be able to do this coordination. So there are these two components, and they're quite important in both of their independent ways, but Sean and my project focus much more on duplication of function. And this is because these kinds of collective action problems are most severe in rapidly growing cities, especially those where the urban system and the political system might suffer a bit of mismatch. So what do I mean by that? How the urban system and the political system might be mismatched? Well, this is an example of the city of Bristol from space. It's a satellite image, and I've overlaid it with the population of this area from World Pop. The different governmental units that are responsible for coordinating, planning, permissioning developments in this urban area are shown in pink. And you can see that one kind of continuous splash of population is split across three different councils, three different planning agencies that all have to work together in order to govern the population just in this one urban agglomeration. So this is that kind of duplication of function, this kind of urban fractionalization that we're going to be talking about today. So there's a couple of questions in the literature on urban fractionalization. There are kind of existential, empirical questions. Is authority actually divided between multiple influential agents? If so, how divided is it? Are some places more divided than others? A lot of foundational work on this question still remains to be done across the world. So in our project, we proposed two components. At the time, we suggested a novel algorithm to identify functional areas of cities, or areas of cities that appeared to be kind of all hanging together. And then we also wanted to be able to describe how these cities were split by different government agencies in a duplication of function way. So trying to look at how many different governments you had to interact with to plan in that urban area. So talking a little bit first about the part of the project on identifying cities, city systems are very different in different places and different parts of the world, and they evolve differently over time as well. Here, I'm showing you a picture of an area in sort of central southern Nigeria, a town or conurbation between the town of Onitsha towards the north on the river and a further sort of large colonial town called Owerri on the bottom of the map. And this is the population structure of that area. So you can see that there are a few core older cities that are quite dense and strongly populated, represented by lighter colors in the map. But then there's a lot of sort of higher population sprawl. Lots of population distributed across the map sort of evenly. This is the collection of governments that are responsible for coordinating in this urban space. There are a lot. It's very difficult to coordinate among this number of local councils in this area. So showing Bristol, and there being 3 councils, showing this conurbation is, I think, 6 times larger than Bristol, and yet has way more governmental agencies that are responsible in this sense for planning these different zones. Focusing in on an area that just has about the same population and size as Bristol is the sort of old city of Onitsha. And you can see here, even then, on the left, there are way more governments responsible for this area than on the right. In addition, you can also kind of see that the population data varies pretty strongly by region. So the quality and the sub-governmental unit resolution is way more detailed in Bristol than it is in Onitsha. And this is because of the smoothing intrinsic in these kind of raster estimates of population for the globe. Second, territorial control structures will vary by country. And this is really hard to get at. What a council is in the UK is not the same as what a Bundeslande is in Germany, is not the same as a council or a city council in America. Very, very different things. And further, urban structure itself will vary by city. So some cities are really well represented by their governmental units and some will not be. So in order to kind of get around this, we wanted to come up with an algorithm that could generate urban structures based on satellite imagery without the aid of populations. So here I'm showing you 2 conurbations, which have approximately the same population, the Onitsha and Owerri conurbation that I showed you before, and then the Detroit-Windsor conurbation on the border between the US and Canada. Both arguably are quite fractionalized in their city government, and both kind of have distinctive urban government challenges that result from this fractionalization. To identify the city boundaries, we worked with the European Space Agency and their urban footprint map, which gives you sort of pixel values of either built up or not built up land. And we developed a novel algorithm to generate sort of consistent urban areas, even when the patterns of density were quite different. So same algorithm, no kind of additional tuning, but you can see that the urban areas detected in Nigeria allow for a much different urban morphology than that selected in Detroit-Windsor on the left. And this was pretty useful. This is quite important. We intended to validate this process. And so we had budgeted for a couple different field studies, both of Detroit and of Onitsha. But between one thing and then another thing, we kind of found it hard to get to Detroit to do this study. So we did end up having our research associate, Nick, travel to Nigeria and work with partners in Lagos to try and understand the efficiency of this algorithm. So when we went to validate these urban areas in Nigeria, we talked quite a bit with local academics, with planning officials, some local realtors. And we found that the algorithm worked pretty well in situations that looked like this, where it kind of fits a pseudo-Western model of how we think buildings should work and how we think urban infrastructure should appear. And it also worked for kind of these styles of areas where there was really densely built up stuff that sort of we can understand as a reasonable part of a city. But it also kind of fell apart in other areas unexpectedly. So this is the boundary of one of our urban areas in the sort of Lagos metropolitan area. And we're looking at an area that's not considered in the city. And unfortunately for us, that looks like a city to me. So we found that there were some kind of issues with the edge cases of these kinds of algorithms. And it was really having trouble picking up these kinds of areas, which maybe didn't necessarily look like classical sort of Western cities that these kinds of models were initially trained on. And this is a pretty typical result in the literature. But then we started to see that this is because of the rapid growth of the urban footprint in these areas. So there's a lot of construction occurring. There's a lot of really fast new buildings being made, new developments. And some of those might even look like things that we see in other models of urban expansion, other kind of architectural or cultural contexts. So what we found really is that land speculation and growth is really rapidly changing the structure of the urban environment in these areas that we wanted to talk about. So the problem at the end of the day was not with our computational approach. The problem was actually with our data. The actual classification method used in these systems was not responsive enough for us to be able to accurately characterize the development challenges in rapidly growing areas. So we had to move on and adopt a little bit different of a strategy. Instead of sort of focusing on identifying the cities, because we had this kind of data challenge, we focused on talking about the splits. So I recognize that I'm sort of a little short on time here. So focusing in on how to characterize splits, we used the global administrative data set, focusing on the level 2, which is like a subnational governmental unit. And then we used the global human settlement layers definition of urban boundaries, which were a little bit more current, a little bit more useful in this case. And we used a metric that's common in landscape fragmentation studies, where you kind of look at the different polygons that intersect between these two frames of measurement. And so you're characterizing the difference between the fragmentation that occurs in population that's not in the city. Here, this would be the little population bounded by the orange and pink boundaries in the south, and the population up in polygon D. So you're looking at the fragmentation of that versus population that is within the city. So there's a little bit more on the fragmentation index. I'm not really going to go into it, but we're dealing with basically the set of all of the polygons between the intersection of the city boundaries and the intersection of the government boundaries. And we're characterizing them based on the entropy of those two sets of polygons. So we're looking at how the population is distributed. Is it even or is it not over that kind of substrate? And the fragmentation index is just the relationship between the evenness of the whole area relative to the evenness of only the city. So a really simple way to understand this is a city like Las Vegas would have a fractionalization index of 0 because it isn't split by any other governmental unit. Now this is not admitting other kinds of governmentality, but it isn't split by any GADM2 zones. Whereas a city like Dallas-Fort Worth is obviously split between many different counties, which is the level of the governmentality that we're looking at here. So the fragmentation index focuses on how population in the orange polygon and population in the pink polygons kind of overlaps with one another. And when it's 0, it means that, like Las Vegas, we have no splits. And it can go all the way up to infinity, but we have sort of like a midpoint at 1, which means that it's about evenly balanced. So large values mean that the population is more fragmented, basically. And when we look at this structure over all of the different cities in the global human settlement layer, we see kind of a positive relationship between population size and fragmentation, which is what we would expect. Big cities, no matter where they are, tend to get more fragmented by government structures as we go along. So that is quite reasonable. But where things get interesting is that both in African cities and in lower income countries, cities in lower income countries, cities tend to be way more fragmented at the tail of the distribution. So this suggests that the governmental structures in these contexts, in low income countries, in African cities, they do not sort of well characterize the population distribution. The urban structure and the political structure, they do not align. The way that you read these plots, if anyone is interested, is you have, these are called letter value plots. They kind of progressively go up in distribution mass as you go up. I also like them because they look like little skyscrapers. But you kind of see the longer the building is, the more mass of this distribution is concentrated at the tail. So you can see here that the regional diagram in African cities, there are way more African cities that are fragmented politically than in other countries and regions. And likewise, you can see that this is the case for low income countries. Well, let's do a more intersectional analysis and look at how that happens across different sets of income region pairs. In this case, an interesting property comes out that in Asian cities, it is the lower middle income countries that tend to have extreme fragmentation. In contrast, in Africa, it is primarily the low income countries that have the most extreme fragmentation. So there's something going on with the interaction between sort of historical development, regional characteristics, and also the income of countries that's affecting the interaction between urban governance and population structure. Notably, when you look at Europe, you also have a relatively high collection of fragmented cities in these countries. I think that that's pretty reasonable, makes sense. But it's just interesting to call out that that collection of countries have cities that are way more fragmented than the other European countries. So the last kind of thing that was sort of interesting is looking at the distribution of city sizes within regions and looking at their fragmentation. So what this is showing you is that for each region, we've grouped the cities based on their size distribution. So in each region, the largest cities are in blue, and the smallest cities in that region are in pink. What this shows you is that across the board, the biggest cities in each region are more fragmented. However, the biggest cities in Africa are nearly always more fragmented than those elsewhere. They are way more fragmented. You can talk about sort of statistical measures of stochastic dominance, and we see this is statistically significantly dominating in distribution all of the rest of the distributions. It's pretty intense. The fragmentation story here is quite significant in Africa. And that's important because of these kinds of challenges of coordination and cooperation that we mentioned before. As cities rapidly grow, we need to understand how this fragmentation intersects with population growth. So to close up here, we kind of had this project to look at the urban structure, and we also had this kind of component to understand, or at least just descriptively characterize, how cities and populations are split. There's a bunch of different ways that people are drawing cities now, and we'd like to replicate this over those boundary sets. We've done the computation, we just need to do the interpretation. Second, there's a lot of literature on the causal drivers of this kind of fragmentation that we still need to be able to relate. Especially estimates of population structure and change, they vary significantly across the globe in quality. So that one is probably the most interesting to get at, but it's also the hardest to study. Finally, we intend to publish the algorithm, the hierarchical DB scan plus hulling mechanism that we used to document that it is sufficient to identify urban areas across the globe, even when their urban morphology varies. So with that, I'll kind of wrap up and suggest that that's been kind of the high level overview of the Turing Fellow project that Sean and I have worked on with wonderful support from Nick. And I'll allow, I guess, the floor for any questions. Thanks.
Thanks very much. That was a fantastic insight into the project. We do have a couple of questions, and I think we've got time for those. So first of all, the assumption is that the multiple influential agents are not corrupt, question mark.
We are not making any assumptions about the style of government that's being exercised by these agents. And of course, there are differences in those experiences. So as I mentioned briefly in like Las Vegas, there are two different town councils. There's Henderson and Las Vegas. That's fractionalization. It's just not captured in the way that we're measuring it. Likewise, there are different ways in which, you know, corruption and sort of government responsiveness and quality issues, things like this, they do matter. However, systematic data on that information usually is only available at a country level through something like Amnesty International's index. So we can get that, but we can't get it by city. So it becomes a little bit of a pastiche in order to use that information in this analysis. We might do it at some stage, but in general, it doesn't exactly get us what we want. But thank you for the question.
I can take the next one if you like.
Oh, hi. Yeah, sure. So, hello. I didn't see you there.
Yeah, no worries. No, so it's a great question about using nighttime lights. I presume that that's what's meant by nighttime images, but using nighttime lights as an alternative. So one of the problems with using nighttime lights is that in regions like the one that Levi showed in Nigeria, where you've got low density and relatively low income housing, there's not a lot of light. And so you can miss low density, low income areas quite easily. And it's really quite stark in some cases. I was doing some research with Johannesburg in South Africa, and there's a really clear, stark line in the nightlights data between the formal and informal areas on the fringes of the city. So although nightlights are really good for some applications, in this case, what they end up doing is lopping off large chunks of urban populations in low density, low income areas. And further, as I recall, nightlight information is part of the product used in the European Space Agency's footprint. So it's not necessarily that we're not using nightlights, it's just that that data product itself, which includes nightlights, is too old.
Really interesting. Thank you very much, both of you. Okay, if you could unshare your screen and we will move on to next. So we're welcoming Professor Rachel Franklin, who's a professor of geographical analysis at Newcastle University. Rachel, I'm afraid I don't have a title. I do now. Great. Spatial inequality and the smart city. Welcome, Rachel.
All right. Hopefully everyone can see my slides. And I'm doing something similar to Levi and Sean in that I'm sort of reporting on where we are with this project, which started in autumn of 2018 and then was paused for a good year for the pandemic and has now been sort of up and going again for the last 6 months or so. And it's a pretty sprawling project. Let me make sure I can share my, hold on, I'm gonna minimize all the pretty faces. Pretty big team. So we have Kate Robinson, who was the original RA on this project, who's now a lecturer at Liverpool, Kate Court, who's an RSE here at Newcastle, Jack Roberts, who's a data scientist at Turing, and Iman Zeid, who joined the project as the new RA about 6 months ago. So lots of people working on this and lots of things happening with this project. So I'll talk about just a little piece in the next 20 minutes that I think will be most interesting to this audience. And so, of course, this is based on a project that was funded by the Turing Institute. They're really aimed at identifying a particular form of spatial inequality in cities, sort of the intersection between demography and the location of people in the city and sensor networks and where sensors are placed. And the starting point was that Newcastle is home to the Urban Observatory, which is the UK's densest air quality monitoring network, and they collect and stream lots and lots of real-time data on lots of things, not just air quality. And one of the things that was interesting to me as a population geographer was this question about what the purpose of air quality sensors really is. And it seems to me that at the foundation, it's about measuring exposure. And if we want to measure exposure, we need to know something about the coverage for sensors and something about who is located where in the city. And so that was sort of the starting point for the project. There are 196 of these air quality sensors that the Urban Observatory has across the Tyne and Wear, 144, now about 146 in Newcastle. And this was, as I said, sort of the starting point. That if you look at the map of where the sensors are located, it's very unlikely, just from sort of a naive view, that the sensors are providing what we might think of as equitable coverage across different socioeconomic dimensions. And there could be good reasons for this, but we were really hoping to sort of help build understanding and build tools that at least might help make decision-making practices and procedures more transparent and more clear, both to the person locating the sensors and to the general public. And so the first part of the project, about where we were before we stopped at the beginning of the pandemic, was just sort of identifying that certainly in the case of Newcastle's sensor network, sensors tend to be located predominantly in relatively middle income, well-to-do neighborhoods or in the city center, and that the most deprived neighborhoods of Newcastle, even though they have lots of major roads traveling through them, even though they were sites of industry, don't tend to have any sensors at all. And so that leads us to thinking about what makes for a good decision. And I think in defense of the Urban Observatory and for any decision maker deciding about where to place sensors, it's actually really difficult, right? You've got competing coverage goals, and I'll talk a little bit about this, but sensors cost money, right? Even cheap sensors cost money, but the really good sensors are really expensive, and they require upkeep. So it's not that you place them and then you're done with them. And then there are also questions, of course, about demography and spatial sorting. It's very difficult to optimize coverage for different types of groups all at the same time. And then I think that there's also a question, again, about what the purpose of the sensor network is in the first place. Is it about providing reliable data that can lead to good policy making, measuring exposure, or is it more about representation in the city and letting constituents know that their city government cares about them and is collecting information for them, or in parentheses, about them? And so I'm going to talk mostly today about how we can make equitable decisions easier. And this has a couple of moving parts. It actually is, I think, 3 moving parts, but I'm going to talk mostly about just one of them. So one is that, of course, we need to talk to decision makers to understand how the decision making is done, and that's underway. But we're also working on a decision support tool, so an interface to help visualize and work through these trade-offs. That's in process. And then underneath the hood, we have sort of the optimization algorithms that place the sensors and then estimate coverage. And that's sort of mostly what I'll talk about today. And I don't think that the end goal here is necessarily a tool that would be taken off the shelf that would locate the sensors precisely. In other words, you don't use it to tell you where to put the sensors. You use it to give an indication of the trade-offs, to basically work through manually and visually this process of trade-offs, that if you want to cover this part of the city or this subpopulation, you may necessarily, for a given number of sensors, not be able to cover other parts of the city or other populations. Because I think that a lot of this is sort of implicit, because the people locating the sensors are good maybe at air quality and urban climate, maybe at the sensor piece, and a little bit maybe less expert at the spatial demography component. Okay, so this is a very early prototype of what the decision support tool would ideally look like, which is that you would have a sense of what the budget would look like, or a number of sensors that you would like to place, a sense of what you're hoping to provide coverage for. And we focused really on the exposure component so far. So demographic subgroups, whether you're interested in where people are during the day, where they live. And I think that pretty much covers the coverage on the decision support side. But it's really, so the thing that we've been wrestling with from the very beginning is that this coverage is kind of a slippery, it's a slippery concept, and it's slippery conceptually, but also technically. So I'm going to tell you sort of where we are now, but that shouldn't suggest that we have sort of excluded all other ways of conceptualizing and estimating coverage. On the technical side, we have definitely gone sort of an optimization approach. You know, can we come up with the best allocation of a given number of sensors with a particular goal? But on the conceptual side, it is, I think, really difficult. As I mentioned already, there's sort of this hazard versus vulnerability orientation for sensors. Are you hoping to capture where emissions are happening? Or are you hoping to capture who's exposed to those emissions? And they aren't necessarily in the same place. And I should say that we haven't accounted here at all for the fact that people are mobile, which is something that we definitely would like to be able to handle. So you already have a trade-off between hazards and vulnerability, but there's also sort of what the purpose of the sensor network is and how you're going to estimate coverage. And here we differentiate between what we call sort of material coverage goals, which are really about political representation and governance, and individuals who live in the city being able to say that they have a sensor in their neighborhood. This may not produce the best data, but it does account for representation. This is in opposition maybe to more of a utilitarian or a technical goal where you really are caring about evidence, right? And here you could think of deserts as being places that fall outside sensor catchment areas, or deserts being places where the levels of uncertainty associated with the modeling are so high that you're really unsure about what the actual emissions or air pollution might look like. So what we've gone with is something that's a little bit more like material and utilitarian, where we're really interested in the output areas that don't have sensors. So sort of what we've decided on. So we take two approaches for this best allocation of sensors. So this is an optimization problem. I'll first show you briefly a single objective algorithm where we're really just interested in optimizing for one demographic subgroup or total population. So either a sensor network of a given size that aims to maximize coverage of children or the elderly or the workplace population or the total population. And then the part that's really interesting, especially for sort of real life decision-making, which is that you've got trade-offs. And so we have a multi-objective genetic algorithm that we use to represent the trade-offs across these different dimensions. And again, they're all demographic. We assume that sensors would be placed at output area centroids, and then we just have this sort of distance decay function, theta, that can be set to different bandwidths, which maps on a little bit to this conceptual idea of coverage, right? The actual reliability of a lot of these sensors is really small, and we don't, I mean, it's down to like meters. Whereas if you're thinking about coverage and representation, we assume that that would be wider, and we go out to about 500 meters, right? Does it mostly matter whether you're able to see these material objects in your neighborhood as you're walking down the street? Okay. Just making sure I look at the time. So this gives a sense of what networks look like when you compare number of sensors versus this theta, this sort of distance bandwidth. So the graphs on the top are for 250 meters. So assuming a very small, but probably more realistic estimate of where the sensors are providing reliable estimates of the air quality. And for 20 and for 60 sensors. And you can see the C, hopefully you can see my cursor, but the C is showing that for 20 sensors with a small bandwidth, you only cover 18% of the total population, given the assumptions that we've made. Even though, if you go to the bottom right-hand corner, even if you stretch it out to 60 sensors at 500 meters, you cover about half of the population. Now, one interesting thing about the sensor network, the sort of naive sensor network here, is that it definitely provides sort of a more spatially uniform coverage in terms of sensor location. That is, there are more sensors located around the city. And if you're more interested in city residents being able to see that, then this would certainly provide a better estimate, but it's still about half of the population. We have this other problem, though, which is probably not a surprise to anyone, which is that different kinds of people live in different parts of the city. And this, of course, is true on lots of different dimensions, whether it's income or deprivation. Here we focus on age and workplace. Age mostly because it's sort of a primary dimension for vulnerability to poor air quality. So both children and the older population are more at risk for poor air quality. So you would think that you would want to make sure that you had sensors in those locations. And then workplace accounts for daytime population for people who are employed. So we look at that, right? So you can see that if you're looking at Newcastle, and this sort of differences are going to hold across cities, the workplace population tends to be pretty clustered in space. And children and the elderly are a little bit more dispersed, with the elderly sort of more dispersed across the city than the children are. The sort of lighter colors are giving you a sense of where the density of these different groups are, right? So the real challenge is on the fringes of the city where you have really low population density, even for the total population. And it's costly to place one sensor there because you're not really covering that many people in that part of the city. So there is sort of an incentive to locate the sensors closer into the core of the city. Okay, so just to give a sense of what these trade-offs look like, we take two extremes. So on the left, we have the elderly population, so 65 and up, versus the workplace population. And on the bottom, let's see, well, if you look at the right, on the right-hand side, this is both for 60 sensor networks, one for at the top 250 meters and at the bottom 500 meters. With the workplace population with 60 sensors at 0.5 kilometer, you can get to 80% coverage of the population because the workplace population is so centralized. Whereas for the elderly population, with 60 sensors and 0.5 kilometer, you're at about half of the population. And if you look at the locations of the sensors, the dots on the map, you see that the patterns are different, right? So you have a trade-off, a choice that has to be made for 60 sensors about whether you're going to prioritize coverage of the elderly population or coverage of the workplace population. Okay, and you can imagine that were we to include lots of different layers for different socioeconomic groups or demographic subgroups, that this would become even more challenging. Okay, so can we identify compromise networks, right? Maybe it doesn't have to be the very best for any one subgroup. It just has to be good enough across all subgroups. And that might be a suitable solution to where to place sensors. And so what we do here are 55 sensor networks for reasons that will become clear in a moment. And what this graph is showing is that we can, for 200 estimated networks, assuming that we just need a 45% coverage rate, we can come up with 62 that will be suitable across all 4 dimensions. So there would be some solutions, but you can see that if you're even hoping to get to half of the population, your choices become really, really small, not because of the workplace population, but because of the concentration of children and elderly. So we're not even in the realm for these other groups of covering 70 or 75% of the population. So here where we talk about being satisfied, we're being satisfied with a relatively small share of the population, but across a variety of demographic subgroups. And so this is an example of what one of those networks would look like. Again, a fairly dispersed network relative to what we actually see on the ground, covers about half of the population with 55 sensors. So to go back to the Urban Observatory, which is an actual existing network, how does our approach compare to sort of their ad hoc approach to placing sensors, which I'm happy to talk about, because this isn't meant at all of a critique of their approach, simply a comparison between what would happen if we tried to sort of automate and make explicit the choices of placing sensors relative to sort of an ad hoc approach that doesn't take population distribution into account. So the 146 Urban Observatory sensors, we snap those to the 55 output areas in which they're located. So even though they have vastly more sensors than we've been working with for our estimated networks, they're actually in relatively few output areas. That's where the 55 comes from. And then we estimate coverage with the same approach that we use when we place our sensors. So if you look at the top, at 500 meters, so anything smaller than 0.5 kilometer, of course, is going to dramatically shrink the coverage that you're getting for any of these groups. It's a little bit more than 1/3 of the total population that's covered with the Urban Observatory network with all of these sensors, and about 1/3 of children and elderly populations, and about half of the workplace population, which makes sense because so many of the sensors are located in the city center in Newcastle. We then sort of compare areas of the city that are arguably overserved or underserved. So anything in orange are areas that are underserved by the existing urban observatory network. And these areas are largely poorer, but also areas of the city with older population and just general total population. But there are these purple areas that are, yeah, right. There are these purple areas that are arguably overserved or overcovered, and you can see those sort of in the city center, but also, yeah, also in other parts of the city. So you could think about taking, for this given number of, say, 150 sensors, spreading them out more widely, and you could imagine getting really good coverage that way. So this compares the Urban Observatory network to what we have. The horizontal line here is the Urban Observatory coverage for each one of these demographic subgroups. So it doesn't really top even 40% for anything but workplace population. And these blue networks, the blue dots, are the ones that perform better than the Urban Observatory across all 4 dimensions. So it was pretty clear in the previous graphs, just by automating sensor location with only 55 sensors, we could get performance. If this sort of coverage is what you're looking for, we can get coverage that is much better than what is actually happening right now. So we've got some next steps. We've got about 6 months more on the project. And as I said at the beginning, we're sort of working on three different tracks, right? So one is additional interviews and user testing. So the interviews are with decision makers at city councils, sort of walking through how decisions are made about what kinds of sensors, the number of sensors, the placement of sensors, talking to citizens and residents about how they feel about both hazards, but also sensors, and then user testing for the decision support tool. So lots of prototype testing, but also working on increased flexibility for the decision support tool. And that's not just more layers, it's also user-generated networks, or what happens when you sort of prioritize 2 or 3 different subgroups and you see what the network looks like on your screen, and you would like to just move a few sensors to see what happens to coverage, right? So we feel like that's something that's really important that users should be able to do, sort of in real time, manually move sensors around and then re-estimate coverage. Finalizing the sensor network optimization package. So right now, everything has been sort of fine-tuned to work well with Newcastle and Gateshead, but of course, there are lots of cities outside of the Northeast. And so ideally, this sort of optimization package should be flexible enough to work with any location, certainly, hopefully any location in England or the greater UK, but ideally much more broadly than that. So that's something that Jack is working on pretty hard right now. And then at least trying to think a little bit about the air pollution source, right? The hazard challenge, because right now we've really focused on vulnerability in people, which I think made logical choice because that sort of reflects my background and my interests, but exposure is really key. And to do that, kind of tricky because you have to estimate what hazards look like. And so one thing that we're exploring right now, so this is a little bit what the decision support tool looks like at the moment. So layers where you can sort of illustrate what the fabric of the city looks like in terms of deprivation, for example, or health, but then the demographic subgroups, current location of urban observatory sensors. But what we're exploring right now is sort of the use of space syntax to give an estimate of what traffic-related emissions might look like given the way the street network is constructed. And so this is sort of exploratory. I'd be keen if somebody has a clear idea of alternatives. I'm hesitant to use traffic cameras because they sort of, I think, face similar challenges to the challenges that we see with the air quality sensors themselves. But I'd be really keen to hear about that. And we're also interested in embedding movement and mobility, right? So if you think about a sensor having a coverage area, right? There are where people are during the day if they don't move, where they are during the night if they're not moving around. But of course, lots of the population is mobile during the day. So you could imagine them sort of passing in and out of coverage areas of different sensors. And lots of people are interested in this from a public health standpoint, right? It's about what are our denominators for estimating exposure to poor air quality. And so just some last takeaways before I stop. So some of this is just practical. I mean, there's the technical components that I find really interesting, and I have found the team aspect of this project to be fantastic and very fulfilling. But a lot of this is just practical, is that when it comes down to actually making decisions about where to place sensors in smart cities, there's so much uncertainty, but also so many trade-offs. And I think this is an important element of the conversation, where we tend to assume that decision makers, if they make poor decisions, it's due to bias that's either explicit or implicit. But actually, it would be really difficult to place a reasonably sized sensor network that would actually be fair or equitable to everyone. So that maybe transparency is the way to go here. So at least the audience understands why you've made the decisions that you've made, and you're able to talk through the decision-making process. So I think rendering the decision-making transparent is really important here. And that there are lots of challenges related to spatial unevenness and inequality. And when we talk about smart cities, I think, interestingly enough, it tends to be talked about a lot sort of aspatially, but actually a lot of the challenges that is where the equipment is placed and who it's gathering information for. And we tend to talk about the negative elements of this, right? Surveillance, for example, but there's a plus side to it too, when you think about air quality or other forms of sensors, that we tend to gather important information for some groups more than for others. And then finally, just as multiple means of coverage, which we're still kind of wrestling with on a daily basis. And that's it.
Thank you very much, Rachel. Bang on time, and we've got time for some questions. There's one in the chat, and then I have to admit I have one for you as well, but let's go with the one in the chat first. This is from Anonymous. Could you tell us a little bit about how the locations of the sensors in the current network were decided?
So it's a combination. When we interviewed people in the Urban Observatory, the phrase that was used most often was ad hoc, right? So you can't place a sensor wherever you would like, right? So you definitely can't place it at the centroid of an output area usually, but you also can't just place it anywhere you would like on the street furniture. You're very limited in where you're allowed to place these sensors. So that limits locations from the get-go. Another tricky element is that these are very expensive pieces of equipment that require upkeep. So of course they need to be accessible, not just the ones to install them, but sort of repeatedly for calibration. And there are some parts of the city where they're safer than others, right? So you place a sensor and then it gets things thrown at it, right? Or it gets set on fire. And this is another reason why the actual outreach component for this sort of work is really important, understanding how residents in different parts of the city feel about this kind of equipment, and sort of making sure that there's a conversation between, you know, these decision makers, however you want to cast them, but also the people for whom the information is being collected. But yeah, so sort of a combination of where is the equipment safe, where do we need to have sensors to meet sort of air quality guidelines. So there are certain parts of the city. One of them is on this slide right now, right? You can imagine that at rush hour, this bridge is pretty full of cars that can't move. So of course you need to place sensors there, right? So you use up some of your degrees of freedom on your sensor count for the places where you know you need to have sensors, which doesn't necessarily leave a lot left over. And then finally, this is turning into a bigger answer. Then there are the parts of the city that demand to have sensors for air quality, right? Sort of the inverse. And that's one reason why you see some of this density. Well, one reason you see density of air quality sensors in sort of one of the more well-to-do parts of the city is that paradoxically, it's relatively wealthy, but also has poor air quality because the Great North Road runs smack through it. So there are these sort of interesting reasons why you see sensors located, but people demanding to be covered is also one reason why you don't get this sort of uniform distribution. Hopefully that answers the question.
Thank you. Second question in Slido says, this is neat. The coverage area movement is a great way to go. Have you explored using proxies for daytime population like footfall or travel to work data?
So we use the, the daytime workplace population for that workplace, but it's only going to cover people who are sort of employed during the day. We have discussed looking at schools or care homes, these sort of other proxies for where at least children or older populations might be during the day. But that's kind of as far as we've gotten with that. I find it, I find it challenging because finding data on actual mobility, that is, I shouldn't say it's not a challenge. What's a challenge is knowing who it is that's doing the movement, right? So footfall isn't a problem. We've got great footfall estimates from the Urban Observatory. They're really good at this. And they had some fantastic graphics during the pandemic that sort of looked at what happened to footfall across the city as lockdown sort of rolled out. But you don't know who those people are, right? And so you're making extra guesses. And I suppose this tells you a lot about who I am as a researcher, but I really don't like it when I have sort of assumption upon assumption upon assumption, and then I'm just making a wild guess. I'd rather do what I feel like I can be reasonably confident in. But we would love to know not only where people are during the day, but also sort of these activity spaces of people as they're going about their day and how they're moving in and out. I mean, this is similar to what happens in epidemiology or public health, the idea of people sort of accumulating exposure to poor air quality as they go about their business throughout the day and across weeks and months. They move in and out of poor air quality areas. This is sort of moving in and out of sensor coverage areas so that you can build a composite picture of who you're actually providing coverage for. That to me is a really exciting avenue, but not one that we've been able to make a lot of headway on.
Great, thank you. And then we've got a question from Daniel Wilson. Could you please say a bit more about incorporating space syntax as a tool into your analysis, e.g. the affordances, limitations?
Well, since we've only just started it, and I'm not the expert on this, I'm not able to say a whole lot, except that we're still exploring whether we feel confident that it at least seems to provide the same degree of certainty that the traffic cameras do when they're estimating traffic throughout the city. I mean, this is the same challenge as mobility, in that the way we estimate emissions tends to be from a set of points and then generating a surface, and then you sort of estimate what the air quality must be in particular locations. So we have a pretty good idea for some major intersections, for example, where air quality is really poor, but it's sort of what happens on the back streets that to me is an important, especially if you're assuming that people are kind of home during the day, that is an important element. So the space syntax, because it's looking at connectivity across different levels and types of streets, can give you a sense at least of what kind of throughput you could have or potential that you have for movement through an area. So sorry, I wish I could provide a more detailed answer to that. Maybe if I give another talk like this in 3 months, I'll have more answers for you.
No, that's great. And just really quickly from me, a question from me. So I know this is outside my comfort zone, but I've done a little bit of work with Transport for London. I'm aware of other kinds of sensors, which made me think about the kind of ecosystem of sensors. And I'm thinking about, so London's got some air pollution monitors on Google Street View cars, and so there are mobile sensors and indoor sensors. And then I started thinking about the sensors that Public Health England have got around UV and noise. So yeah, I just wondered, what are your reflections on how the kind of approach you could be taken could be broadened out to those kinds of sensor ecosystems?
So my general sense, and this is kind of a big picture, big idea response, is that I think that this research reflects a very particular time period of smart city research, sort of where we are at this moment, which is that we're still very much working with kind of fixed infrastructure and people who move. But the technology is going to improve, and I think it's improving really quickly, to the point where you could think about either increased numbers of fixed sensors, but actually something that is much more mobile, right? And then I think the potential for research, I think, becomes kind of fascinating. If you're thinking about the purpose of sensors for policy evaluation, for example, like what happens when you impose congestion charging for part of the city. That is a really interesting research design, whether your sensors are fixed or mobile, because you need to be able to say something with confidence about the before and also about the after. So I think that this research, I mean, I hope it lasts, I hope it endures, but I think it's reflecting this very particular time that we're at with sensor technology. And I expect that in mere years, we'll be able to do a lot more with different types of sensors that can provide sort of high quality real-time readings of lots of different environmental variables.
Really fascinating. Thank you very much. Okay, we could talk for ages, but we have another exciting talk to move over to. So it gives me great pleasure next to welcome Dr. Jack Stilgoe, who is a senior lecturer in the Department of Science and Technology Studies at UCL. Jack, over to you.
Thanks, Kate. Hello all. Thank you for having me. So my discipline, my talk is a little bit different. I'm just going to try and share my screen. So I'm one of these odd Turing fellows who sort of comes not as somebody doing, oh, hang on, where's that gone? Not as somebody doing data science and artificial intelligence, but somebody problematizing data science and artificial intelligence from the perspective of seeking to govern new technologies such that they are aligned with the needs, hopes, fears of society. So I'm in the Department of Science and Technology Studies at UCL. My work is funded by the Turing Institute as a project on trying to connect machine learning with what I and other social scientists call social learning. It's also part of an ESRC project called Driverless Futures that I run, looking at the anticipation of the politics of self-driving cars, and a European project called Scalings, which is looking at urban and other experiments in the real world and how we might govern those. I won't say too much about the particular perspective of science and technology studies. Suffice it to say that I'm interested in qualitative methods that seek to anticipate possible futures, that seek to democratize those futures, so introducing public views into conversations that can be very expert, and working with policymakers. So one of the things I'm doing right now is working with the government's two centers, one the Center for Connected and Autonomous Vehicles, one the Center for Data and Ethics and Innovation, to think about what rules might we need to govern this new technology. The sorts of questions that people like me in science and technology studies ask are this sort of thing. I have a little book that came out last year where I try and describe, the challenge of not just taking science and technology for granted, but asking how science and technology can be redirected in ways that better reflect the public interest. Let me just, because I'm in a sort of urban analytics forum, let me start with reference to a historical example that I think contextualizes my and my colleagues' approach to a new technology like a possible self-driving car and what that might mean for cities in particular. So when new technologies come along, they are often accompanied by utopian promises that presume a certain neat and tidy world that very rarely plays out like that way. So this is from a trade publication at the dawn of the motor car. The promise of the motor car is that it would offer substantial benefits to cities, but also that it would solve some of cities' problems. In the case of horse-drawn vehicles, right, the problems were ones to do with manure, to do with horses not doing what they're told, and occasionally, bolting or kicking somebody, right? So they were seen as dangerous, chaotic means of transport, and they were seen as messy. The as I will sort of explain, the narrative around self-driving cars has a lot of echoes with that same sort of talk. And in reality, what we see with new technologies is something rather different, right? With the arrival of the motor car into cities in the early part of the 20th century, we saw a power struggle, and as an attempt to resolve this power struggle, who should own the road and who should roads be for, we saw the motor car lobby, in effect, persuade and harass pedestrians out of the road in many American cities. The UK cities, it has to be said, took a rather different approach. We didn't legislate against jaywalking. I mean, there were some attempts to, but they were unsuccessful ones. And so what we see is the promise meeting the reality that the initial set of claims about how a new technology would benefit society changed into a set of demands that if we are to realize the benefits of this technology on society, then society would need to adapt. And I'm interested in asking how, when it comes to something like a self-driving car as a test case for machine learning in the wild, how we might see that similar sort of debate play out. So we just brought out a paper in Social Studies of Science that uses the juxtaposition of this sort of idea of autonomy that I will explain in a bit, and then considers all the various ways in which something that claims to be an autonomous technology is actually attached to various social and technical things in ways that we should pay attention to now so that we can make good decisions about that technology. So I'll start off by just explaining a bit about what that narrative of autonomy means, and then based on the interviews that we've been doing with the developers of the technology, you know, what these attachments mean and why we should care about them. Okay, so if you look at one of the currently leading autonomous driving companies, they call themselves an autonomous driving company rather than a self-driving car company. They have this narrative of being able to develop a technology that is a sort of always and everywhere unconditional technology. This, you know, in the hands of a technological vanguard like Elon Musk, gets turned into a particular version of hype and a sequence of outlandish predictions about when this technology will be able to arrive and change our lives, right? Now, the point, the criticism of this should not be he's not very good at sticking to his deadlines, right? The criticism of this might be, well, what sort of political move is he trying to do? What sort of claim is he staking on the future in making these predictions for his, in this case, Tesla's autopilot and full self-driving technology, right? It's rather easy to look at the claims made about self-driving and say, oh, well, they haven't come true, right? It's all a lot of hype. But we want to be a bit more detailed. We want to be a bit more detailed than that. So we've been looking at crashes that have happened involving self-driving cars. So I've done analyses of the Tesla 2016 crash, the first time that somebody died thanks to a computer-driven vehicle, and the Uber crash in 2018, which was the first time that a bystander got killed by a computer-driven vehicle. Less dramatically, but I think just as interestingly, we saw at the Paralympics an encounter between a supposedly autonomous shuttle and a Paralympic athlete who was visually impaired. And this was, you know, embarrassing for Toyota, who were testing these vehicles. But the response revealed something quite interesting, which is the response revealed an admission that actually, you know, the claim of autonomy in that this was a computer-driven object that was independent of the world around it, or at least able to interpret the world around it as a set of passive constraints, was in reality impossible, right? There was a recognition that pedestrians would be expected to do their bit, and that there would be infrastructural requirements to get this technology to work. And yet we see this, the narrative of autonomy in which a computer-driven car would be able to navigate the world independently of first its drivers, right? So the idea of emancipating the machine from the human is sort of one of the driving forces of the technology here. Independently of place, so the idea of that you could emancipate vehicles from geography, but there's also a political sense behind the narrative of autonomy, which is that innovators should be left to get on with innovation, and that regulators should play no part in this. And I think it's important to remember how new that narrative, right? For most of the history of self-driving cars, automated vehicles, the presumption was that the world would need to be rebuilt such that it could be automated. So if you look at Norman Bell Geddes' Futurama exhibition for General Motors in 1940, the idea was very much that automation would happen via roads rather than via cars, that you would have smart places rather than smart cars. And the fixation on the smart car owes itself to relatively recent developments like this one. Oh, the video is not playing, so you can't see those cars just shuttling around that ersatz city. Right, DARPA's initiative was to stage a set of competitions in which cars would be expected to navigate environments independently. And this began with a military motivation to be able to, in effect, navigate unfriendly and unfamiliar terrain. The competitors in those challenges, those grand challenges, went on to populate many of the startups that now are doing most of the running in this debate, including Google's self-driving car project, which began testing in plain sight on the streets of San Francisco and Silicon Valley, and then became Waymo, the company that I mentioned earlier. So from the perspective of STS, of a science and technology studies researcher and a theorist, how might we engage with this narrative of autonomy? Well, I guess the first point is to say that autonomous vehicles, so-called autonomous vehicles, look heteronomous in various ways. They're not independent. They are driven by human desires and motivations, and they are dependent upon what we would call socio-technical systems that in some cases are enormously complicated, but that there are all sorts of reasons why innovators might want to make claims to autonomy in order to secure financial and social capital. The narrative of autonomy has already infected the governance debate around this technology in ways that I would argue are deeply unhelpful. So there's been already a lot of enthusiasm for self-driving cars as a test case for ethicists' favorite thought experiment, the trolley problem. And the conclusion that my colleagues and I would reach is that actually the ethics of this technology will be defined not by, extrapolating from these claims to autonomy, but by engaging with these with the attachments of this technology, the various relationships that define its constitution and innovation around it. And we can think about these attachments in various ways. And these ideas all come from more than 50 interviews that we've done with innovators and stakeholders, asking them, in effect, what relationships define their work in developing self-driving technologies. And you start to see the contingencies of things like hardware, right? So vicious debates within the community about which sensors are appropriate in order to be able to detect the world around them. And once you have these sensors, how do you maintain these sensors? This is a lovely illustration of technological fix to a technological fix that is used by Waymo, right? How to clean a sensor when it gets bird poo on it, right? And you start to see that, you know, just presenting the technology as being artificial intelligence, right, is to ignore the sort of attachments to hardware on the car, but also hardware outside the car. So this was, these pictures are from a trip that I took in a self-driving shuttle in Rhode Island. And I wanted to know how the car saw a traffic light, right? And so from the narrative of autonomy, the answer would be, oh, well, we just do what humans do, right? Humans use their eyes. So you have a camera that looks at a traffic light and sees what the color and location of that traffic light is, and you interpret that information, which, if you're a digital system, is frankly bonkers and prone to being rather brittle. So it's far easier for the traffic light to just communicate directly with the vehicle, but that requires the addition of a little widget, which you can see on the right-hand side, to a piece of street furniture, right? This relatively modest infrastructural upgrade that makes life easier for a self-driving vehicle. And it's one of those things that is revealed in private, if not talked about very much in public. Similarly with high definition maps, right? The way that autonomous vehicles depend upon extremely detailed maps in most cases of the areas around them, which allows them to, in the words of one of our interviewees, know what's around the corner, but also introduces new risks. If the world changes, right? If a tree falls down or a traffic light fails, these systems were described to us as extremely brittle and demand new forms of mapping and remapping all the time. Making these sorts of things work and making the testing of the technology work requires all sorts of hidden labor that, again, isn't discussed very much from the sort of AI-centered narrative of autonomy. We have all been involved in a modest way in this process of hidden labor. Every time we click on one of these recapture things, we're doing data labeling. It's why so many of the images are road-based images. It helps make those categories slightly more resilient. But also we see hidden labor in the safety drivers that are expected to scaffold the testing of the technology while it's in its prototype phase. We in science and technology studies would actually argue that technologies were always in a prototype phase. There's never a sort of testing then deployment line that we can neatly draw. And then, of course, oh, that one's not playing either. That's fine. We can categorize the relationships between autonomous vehicles and other road users, right? A set of extremely complex conversational relationships that we all observe every time we are on the road, but which must, to an autonomous vehicle with its sensors, be turned into a logic of sensing, predicting, planning, and acting, right? So in effect, other road users must be treated as passive rather than as active conversational parts of the system. So how did innovators deal with these attachments? Well, there are a few strategies, and these strategies point us to some important political debates down the track. And I'll just end with this. The first strategy, right, recognizing that as innovation proceeds and as investment plows into this area and as tests scale up, the people involved are now admitting that it is, far harder than they thought it would be, and the sort of easy thing, the easy excuse is, oh, the world is a hard place. The STS response would be to say, well, that's because you were ignoring some of these complexities and these attachments in order to secure the capital that you needed to earn your place on the road. There are still some in the community who say that these are, all of these relationships can be sorted out with just brute force, more computer power, more data, more edge cases built into the model, and we can sort this, right? We can, in effect, learn our way through the world's complexity. There are some who admit that geographical boundedness will define the technology forever, right? That places will, that technologies will always be defined by places, and in particular by what the developers call operational design domains. So not just locations, but also weather conditions, the behavior of pedestrians and other contingencies. And therefore the task becomes, in the words of one of our interviewees, solving the world one place at a time, right? Which already is a big shift to the conventional way in which we think about the rollout of digital technologies. You know, this is not just an AI algorithm that can be scaled almost infinitely at zero cost, which is a sort of a mode of innovation that Silicon Valley is more comfortable with. And then there are some who, admit that if this technology is going to change the world will need to change and meet the technology halfway. And this is described by some in STS as being a project of heterogeneous engineering, that it is never just about introducing a technology in the world to solve a particular problem, right? The world needs to adapt as well. And this is a fairly fundamental challenge to the idea of artificial intelligence as a technology that can adapt to solve our problems, right? And so this might play out politically in terms of the demands on segregated lanes, for example, for automated vehicles, or for additional infrastructure upgrades, even something modest like, ensuring that white lines are painted regularly to ensure that they can be easily detected by sensors, right? The various ways in which the world might be under pressure to become more machine readable is likely to become politically contentious. And then finally, sub-admissions that actually pedestrians are going to must learn how to behave around this technology, as was the claim at the Paralympics. That, as with cars in the early parts of the 20th century, pedestrians need to do their bit to ensure the safety of all of us. And any of us who've looked at urban geography know that all of these things are potentially expensive and potentially extremely contentious. Just look at the debate currently happening in London about low traffic neighborhoods, about the design of a cycle lane, to know quite how politically contentious this potentially is. I'm going to stop there, so I hope we've got some time for questions, but thank you very much.
Thank you very much, Jack. Yes, we have some questions that have cropped up already. So first of all, what about road blockages, potholes, unrecognized images by the system?
Yeah, so I mean that I would add as one set of sort of infrastructural attachments that any developer needs to be able to account for, right? And one way of accounting for them is to say, oh, we just need to map and remap, right? So that we can know the world around us and be able to predict. There is, I think, a more complicated engineering question, which is how do you deal with the inherent uncertainty of not knowing what's around the corner, right? So building in the possibility of a pothole or a traffic light post falling down into your model, rather than just building in the certainty that there is a pothole or a traffic light that's fallen down. So this is just one of many attachments that makes the job of getting this technology to work so much harder than it seems.
Thank you. And another question from Daniel Wilson: to what extent does focusing on the operational difficulties of AVs distract us from the political economy which underpins their development?
I think it's a great question. I don't think it distracts us. I think it empowers exactly that discussion, which is why I'm interested in trying to inform that discussion. I think it's key to be able to understand exactly as Daniel puts it, the political economy driving their development. Which at the moment, you know, developers, it's quite interesting that they find it hard to admit. So one of the attachments that we might want to draw and analyze is an attachment to a particular business model. And it's extraordinary how little thinking about the business model there is. How do you monetize a system involving even driverless transport, right? The sort of idealized version is, oh, well, the political economy, you know, we can tell a story about political economy that is, say, in Uber's case, once you remove 75% of the cost of every ride paying the driver, then you can massively scale up your service. Now, if we pay attention to the actual attachments of the technology, we can see that that model looks, I mean, utterly ridiculous, right? There is no way in which you can just cut those costs. The people don't disappear; they move elsewhere. So this is, I think, one way to understand the political economy driving the technology and seek to offer alternative political economies that might actually be genuinely beneficial for cities.
Great, thank you. And a final question, quite a no-brainer, but what if the autonomous system crashes and I do not know how to drive?
Yeah, absolutely. I mean, if the system is predicated on autonomy from a human driver, right, which some of them are. So if you get in the back of a Waymo at the moment in Phoenix, some of the Waymos are genuinely driverless. They don't have anybody sitting in the front seat. And there is no way that you can, as the user of that technology, drive the vehicle. So, I mean, less if it crashes, because these things tend to be super, super cautious. The more likely thing, and the thing that happens relatively often in those vehicles, is that they encounter a situation that they don't know how to deal with. So they might encounter a construction site and just stop, right? And then somebody from Waymo needs to take charge of the vehicle, reprogram a route around that object. You know, meanwhile, traffic is backing up and all the rest of it. So Waymo's response to that exact question is, well, you can't, and if you could take charge, then that would be dangerous. But if you look at, you know, what Tesla are doing, Tesla are saying, in effect, this is, you know, just another technology that we can add to a conventionally driven vehicle that, you know, is a driver's technology that just makes their lives easier. So whether, you know, the technology is sold to drivers or to non-drivers becomes part of the possible political economy of the technology.
Absolutely fascinating. Thank you very much. So bang on time. Very grateful to all our speakers for being such great timekeepers and also for presenting such fantastic work today from across the country. So it's been a real pleasure on behalf of everyone at Bristol to be hosting. Many thanks to the team in the background that makes it possible, Lily and Patty and the data science team as well. Thank you to our speakers. So thank you to Levi Wolf and Sean Fox and their team. Thank you to Rachel Franklin, and thank you to Jack Stilgoe that we've just heard. If you enjoyed these talks and you would like more, same place tomorrow at 10:30, you can come and enjoy our data-centric engineering seminar series that also starts at 10:30. So please do register for that as well. Thank you, everybody. Nice to see you. Hope you have a great day. Bye then.